All right, guys. So in the last section, we took a look at the instantaneous power that was either generated or dissipated by uh, a circuit that is undergoing sinusoidal steady state. And through a series of trig identities, we came up with a final expression that contained a total of three terms. And now we actually want to start taking a closer look at those three terms and what they actually mean, right? So this next section is going to be on average or real and what they call reactive power. Now, in last section, if you'll recall, we had a network here with two terminals. We had placed a sinusoidal voltage across the terminals, and there was a sinusoidal current that was drawn. Now, we did calculate the instantaneous power as the product of the voltage times the current, where the voltage again was sinusoidal, was of the form with an amplitude, was the cosine of omega t plus its phase angle, the voltage phase angle, and the current was also sinusoidal, so it had its amplitude, had the same angular frequency and time dependence, but it had its own phase angle, theta sub I. And this equation, this tiny little equation, through again a series of manipulations, could be rewritten. So we rewrote equation 1 as, and brace yourselves because this is going to be quite large. The power was the product of the magnitudes for both the voltage and the current divided by 2 times the cosine of theta v minus theta I, followed by v sub m I sub m over 2 again, times the cosine of theta v minus theta I, times the cosine of 2 omega t, and there was one last term, v sub m I sub m over 2, now times the sine of theta v minus theta I, times the sine of 2 omega t, like this. And this is the expression where we left off. Now, there are a few observations that I really want to bring to your attention. The first one is this is a time-evolving power, right? It is a function of time. However, the only places in the entire equation where there's a time dependence is right here in the second term and right there in the third term. Notice that this first term contains no time dependence whatsoever. Right? It is a constant. On top of that, when you take a look at the three terms themselves, notice that the first two terms contain a multiplicative factor in common. In fact, the Vm times Im over 2 times the cosine of the difference of the angles between the phase angle of the voltage and the current, not only does it appear there, but it also appears there. Right? This leads us to two definitions. The first definition is that of the average, sometimes called the real power. And the symbol that we have for it is the capital letter P. And by definition, it is V sub m times I sub m over 2 times the cosine of theta v minus theta I, like this. The second definition is that of the reactive power. The symbol that we have to denote reactive power is Q, and by definition it is V sub m times V sub I over 2 times now the sine of theta v minus theta I. Notice that with these two definitions, right, we can use them in the equation for the instantaneous power, and we can rewrite it in the following way. So with these definitions, equation 2 can be rewritten or just written in the following manner. I'll go to this equation 3. The instantaneous power is equal to P plus P times the cosine of 2 omega t, followed by minus, the minus sign is important, minus Q times now the sine of 2 omega t. And what we actually want to do is we really want to investigate what this equation is actually telling us in terms of the nature of our system. And it's most easily explained by taking a look at a purely resistive load, at a purely inductive load, followed by a purely capacitive load. So this equation itself will have a certain type of behavior depending on the load that you're actually taking a look at. Right? And that's what we're going to take a look at next.